Hello everybody. Today we talk about the origin of the magnetic field. It's in order to understand Maxwell's equation. This is actually you can just take Maxwell's equation as is without having a deep understanding, but my intention is to give the very deep understanding of entire equations. So in the previous video we went through this divergent D equals Q. This is charge density, and this fundamental law comes from the Coulomb's law. The Coulomb's law is going to bring in this Gauss law, and the Gauss law of magnetic field is 0. And what the magnetic field is defined by some kind of the current flowing, and magnetic field is formed around it. So it's a magnetic field is either circular field without any source or drain. Now there is the magnet and can have M plus, M minus, but we talk about this inside the magnet. There is the M plus, M minus. In this case it's opposite, M minus, M plus. This dipole exists and it's all connected. So this magnet exists only with dipole. And what dipole is if you look at the quantum mechanics level, the atoms and electrons wave is moving in one direction, and this is the current, and this current create magnetic field. Okay, so this is the actual dipolar magnet dipolar. So even this magnet, it's actually same as the current generating magnetic field. Okay, so when you say current generates magnetic field, how do you know there is such a thing like the magnetic field generated by current? Okay, this is merely illusion. It's a magnetic field doesn't exist. It's just mathematical presentation of this electric field, which is based on Coulomb's law. This is a fundamental law, and magnetic field is generated. It's just conveniently we assume magnetic field, then equation looks more symmetric and easier to express entire mechanics of the electric field. Say we have a J current flowing, and that means electrons running this way, right? And you take this point and you have Q, say positive ion, moving at the velocity v. Okay, so it's strange things happened. This velocity near this current is gonna generate a force. Okay, and that's called the Lorentz force. And Lorentz said force is two component. This is the electric field, right? Charge times electric field. and here there's no electric field. And another one is a magnetic force. Okay, magnetic force, the Lorentz assumed this J generate magnetic field around, okay, and the direction is like the famous right hand rule, right? When the thumb is showing the direction of current, then other fingers are showing the magnetic field generated. Okay, so this magnetic field and V times, so force go to the inward. Okay, and this is just merely the Lorentz. That time we didn't know the Einstein special relativity theory, and if we use a special relativity theory, you don't need the magnetic field to explain this Lorentz force. What it is when this charge is moving a Q and E is moving very fast to the opposite side, then total speed is E plus V. Then what's happened is the relativity theory said for this Q, this whole flow of electron is contracted. That means the lengths actually get shorter. That means you have a lot of E flowing, and the density, this density here, over here, is going to increase because the density is the total amount of E divided by this length, and the special relativity theory is going to tell you that the length is gonna decrease. That means density increase. That means you have more E negative, and that's gonna attract, because a positive atom is not moving, right? It's moving only V. Only electron moving the opposite direction. So the contraction happened to only E, mostly E. So what's happened is E's density increase. That means there is an electric force, Coulomb's force act on this. So it's actually Lorentz force is a Coulomb's force, and that's why you get this force. So you don't need to say current generate magnetic field. In magnetic field and this charge interact and generate a force. That's the argument by Lorentz, right? And because he didn't know relativity theory. So if you have a relativity theory, you don't need this V to explain this force. There will be force. Okay? So if V is the other way around, then the relative speed become much less, so the contraction become much less. That means the the charges density is diluted and they become less, and that means to move this way. Okay, so force is going to be other direction. So that's the reason we introduce magnetic field, and this magnetic field generated by current, and the magnet, this dipolar is also generated by the current. So it's actually all the magnetic field generated by current is just intermediate stage to explain Lorentz force. Okay, so you can skip this magnetic field, or you can have it for convenience, for mathematical convenience, so that we can write a form, simple form of this force. Okay, so then exactly how much magnetic field we consider to be generated by the current, and that is a Biot-Savart equation. And what happens is, when you have a current flowing along this line and take a point and find out how much magnetic field we consider to be generated by this current I, and this is I here, okay, and integrate along this line the element of the line and external product of the vector r. This is vector r and distance r square. Okay, so this is the equation to tell you exactly how we consider magnetic field is generated. And is it really physically generated? It's not. It's magnetic field defined mathematically here. And this is the way magnetic field is defined. Actually, you can call this a definition of magnetic field. Okay? So the current, and the current can be time variant. So the B will be time variant. Now, so far we talk about time invariant, right? And in time variant, when it's come to time variant, let's see. Maxwell expressed magnetic field is generated around J, okay, and plus there is a time variant factor, and I explain this later. First of all, what this is okay, this is called rotation H, the external product. This vector field is going to work this way. If the current going in, right, this is a J, the magnetic field will be this circle. Okay, if current coming out, then magnetic field is generated this direction. Okay, now this is the right hand law, right? It's a current is a thumb, the thumb pointing a current direction, and the other finger shows magnetic field H generated. And there is another one. This actually is not sufficient to complete the entire electromagnetic theory, because we have a case that, say, we make this kind of ring and apply the time variant like a sine wave here, and this is not connected. That means this is a capacitor, so there's no current flowing here. Okay, but we observe EM wave coming out. EM wave is electric field changing around and magnetic field changing around, a mathematical magnetic field. So we have, in order to complete this math model, we have to add this one. And this is a time variant. When electric flux change by time, that generates magnetic field. We have to add that magnetic field in order to complete, because next equation in the Maxwell is going to be Faraday's law, right? It's induced potential or voltage by change in the magnet. Okay, change in the magnetic field. So change in the magnetic field is going to generate the electric field changes. The electric field changes is going to generate the magnetic field changes, and that's going to change this. Okay, but here you have to be careful. The direction, suppose you have a electric flux and that's increased suddenly. Okay, then magnetic field, this guy, increased suddenly, and this increase is going to cause from this direction additional electric field. That means flux, but it's a negative, so it's called opposite. Okay, so these two equations shows the time variant electric flux will cause the magnetic field. The magnetic field time variant is going to cause the opposite. That means it's react. So what does this mean? It's try to be stable, right? And try to be stable, that means it doesn't change unless you force to change, and you force change by moving this the conductors or whatever is going to generate work. So energy is stable, and this two equations shows energy stays same unless you give some work energy to the system. Then it change delta D and delta E. So this whole thing is it's a dynamic nature. The E change, B change, B change, E change. Okay, it's repeat, but unless it's additional energy coming from this source, like a EM wave emitter, energy source coming from here, then this is going to repeat the process. Okay, so that's a whole Maxwell's equation with math model B. The B or H is the same thing. Okay, so this is a model, math model. With math model, you can have this equation work out. So, but fundamental physical law is a Coulomb's law. There's nothing new. Entire whole things is coming from Coulomb's law. Okay, so electromagnetic field, vector field theory is constructed on top of Coulomb's law, and that's have some fake physical vector field, which is magnetic field. Okay, and with magnetic field, equation looks more symmetric and nicer and easier to do. So it's just a math model. It doesn't mean magnetic field exists. Actually, it doesn't exist. Electric field exists? We don't know. And the Einstein discovered that gravity field is actually the skew of the space. That's great. But electric field, nobody work on it, and we don't know still why Coulomb's law stands. Okay, where it's come from, more fundamental levels we need to know. But this electromagnetic theory as far as Maxwell's equations concerned, it's complete closed theory based on the Coulomb's law. And this theory is very nice symmetric equations, and it doesn't prove that existence of magnetic field. Okay, so in a quantum theory area, there is a string theory, and the string theories bringing more dimensions, like 11 dimensions or whatever the number, keep changing in the theory, and string vibrate in this 11th dimension, not the three dimensions or even 4th dimension, the 11th dimension. Then it can handle most of the quantum very nicely and doesn't prove anything. Just like a magnetic field, its theory looks nice, symmetric, and the whole thing's complete. Doesn't mean there is a magnetic field existing. It doesn't. And the string theory is the same thing. The theory is nice, symmetric, and everything's go well. Doesn't mean string exists. It's not the proof that string exists. Okay? So it's kind of overall picture of the Maxwell's equations and original magnetic field. So I hope you enjoyed this video, and if you like it, please subscribe and wait for the next video.